All right. Welcome everyone to the hardware and computer vision workshop. As the name suggests, this workshop is going to be about two topics. It's going to be the first half is going to be about hardware, where we're going to talk about Arduino. We're going to learn how to program, how to wire Arduino, and the second half is going to be about computer vision, where we're going to be using the OpenCV library with Python. There won't be much overlap between the two workshops. For it's one workshop with the two concepts. Although there are many ways, and I will tell you there are many ways to combine these two topics. In fact, there are many ways to combine just about any two topics, not just in computer science, but in engineering science, computer science, whatever it is. There are many ways to combine topics that you know, and we highly encourage that you do that. It's something that we will look for when judging your submissions. So anyway, let's get started with, first we're going to do the hardware section. And like I said, we're going to be talking about Arduino. So first, a little bit about what Arduino is. Arduino is one of these things right here. This is an Arduino. Arduino is a programmable microcontroller. And there's a reason I said programmable, because there are just microcontrollers on their own that you can't really program. And actually the microcontroller part of this is right here. When you program your Arduino and you upload the code to this board, this is where it's all being stored. And this is where all of the operations are coming from. It's all happening. This is the essentially what a CPU is to a computer is what this microcontroller is to the Arduino. There's some other components we want to look at though. So we have these pins up at the top and at the bottom. You can't really see them that well on the camera, but that's okay. We'll talk about those later when we get to Tinkercad, and you'll be able to see them a little more clearly. So we're not going to worry about that just now. But we have this thing right here, this port. This is your USB cable port. This is, you're going to just take your USB cable like this one, plug it into the Arduino and into your computer. And that's what you use to upload code. That's also one of the ways you can power the Arduino. But when you do it like that, the Arduino is bound to the computer. And so if you just have this on some project that you made and you don't want to have it tied to your computer, you don't want to have your computer next to it in order for it to work, there are other ways to power it as well. With this port right here, you can plug in a 9-volt battery. Actually, the voltage recommended is 7 to 12 volts, but typically you put a 9-volt battery in here, and that works fine. And since the code is already stored on this, there's no need to worry about the code not working. You won't be able to upload code through that because there's no computer attached to it, but you can just run the code fine, and you just won't be able to upload anything. Then there's this button right here in the top, this one that I'm clicking. That is the reset button. What that does is it just resets your code, essentially, as the name suggests. What that means is it'll just start the code from the beginning, so you don't have to unplug the Arduino, plug it back in, or anything like that. You can, if you wanted to start the code again, you press this button, it'll start again. And there are some LEDs. I don't know how well you'll be able to see them. Yeah, it doesn't. You can see them, but you can't really see the labels. So we're gonna go ahead and go into Tinkercad now. We're gonna be able to see all this a little more clearly. So let's do that. All right. So this screen that I'm sharing, this website is called Tinkercad. This is a really good way to prototype any circuits that you're making, not just with Arduino, but any circuit where you're using, actually it doesn't even have to be with breadboard, just any circuit. If you have the components on this side, you can see what components you have. If you have the components you need, this is a great way to test out your circuit. And you have no risk of damaging any components or anything like that. You're free to do whatever you want. This is also really useful when making Arduino code, because we have the Arduino microcontroller here as one of our components, and we are able to program it right in here in Tinkercad. So those pins that I talked about before that you weren't really able to see on the camera were these ones here and along the bottom here. So first I'm going to talk about these top ones, the ones labeled from the 0 to 13. So these pins you can use for output and input. And by that, I mean, you have like output devices like LEDs like we have here, or a motor or anything that's an output device. And you can have an input device like a sensor, or like here you have a potentiometer, stuff like that. Those are input devices. So you can use these pins for either input or output. But you'll see that some of these numbers have a tilde next to them. What that means is that they're able to give PWM signals. And so to explain PWM, well, there are two types of signals. There's digital and PWM. So I'm going to explain both. So digital essentially is just 1 or 0. When you have a digital signal, it's either on or it's off. There's nothing in between. So if I were to use a digital signal on an LED, it's either going to be on at its maximum brightness, or it's just going to be completely off. And you can also have PWM signals, which give a value from 0 to 255. And you can use this to give any kind of brightness in between its maximum and minimum brightness. You can also use this for motors, where you can control the speed of the motor. You can, for a servo motor, for example, you can control its position, stuff like that. And so for analog, or so for digital, actually I should say, I said analog. The reason I said analog is because PWM and analog are the same thing. It's just different words for the same thing. So you also have digital and analog input and output devices. For example, this push button here, you're either pressing it or you aren't. So that's a digital input. This potentiometer, this is a dial. So you turn it from its lowest to its maximum position. Actually, what this is a variable resistor. So the higher, as you move it, its resistance is the resistance it provides is going to increase. And that's how it's able to give a signal to the Arduino. And so that is a analog input. Okay. Now there are some of these LEDs here that I wasn't able to show clearly in the camera. Oh, actually, sorry, I should explain these pins at the bottom. So we have these pins here, the ones labeled A0 to A5. These are used only for input. You can't use output devices with them. And you'll see it says analog in. So these are only, well, you can use them with a digital input, but it's not going to be 1 or 0. It's going to be 255 or 0. Typically, you want to use these for analog input, though. That's what they're meant for. But again, only for input. And it's a good habit to use these for your input devices before you start using these for your input devices. If you have more than 5 input devices, then you can start using, or 6, then you can start using these. But otherwise, it's a good habit to just use these. Then with these pins here, you only really need to worry about these 4. These 2 right here, the 2 ground pins, they're exactly the same. They're supplying the negative, or they're essentially, the Arduino can provide power, and that's how it's able to give power to components. It can supply its own power, but that's limited to 5 volts. It can't give any more than that. There are ways to use components that require more voltage, and we will talk about that as well later. But so you have these 2 ground pins. These are going to connect to your negative terminal of whatever component you're using. And then you have 5 volts and 3 volts. And depending on what components you're using, you're going to pick one. Typically, it's going to be 5 volts. Reason for that is you can decrease the current if, so for example, here I have this LED wired up. The LED cannot handle very much current. If you put too much, it will explode. And so you can limit the current that it has with this resistor here. And it's very simple to do. So you can go have the 5 volts giving a lot of current, and you can bring that current down. But if you go to 3.3 volts and you need something that requires more current, it's much harder to bring the current up than it is to bring the current down. You can see with this resistor, it's very simple. Just the equation: voltage equals current times resistance. So if you increase the resistance, the voltage is going to be 5 volts, so the current will decrease. So yeah, now we're going to talk about these 4 LEDs here that are built right into the board. The first one, this one on the right, is the on LED. When you have, I can actually show you when you have the Arduino is powered. This one is just going to turn on automatically. You can see that it's on. Pretty self-explanatory. Then we have this one. This is the built-in LED. So this is by default connected to pin 13. So you can set up pin 13 to work with this LED. You can also set pin 13 to work up with anything else. But by default, it's on this LED. So you set that up and you use pin 13 like you would any normal LED, except instead of turning this thing on, for example, if I have this connected, it's going to turn this LED on right there. Then we have the TX and RX LEDs. So these will turn on when you have communication between the Arduino and something else. So for example, TX is for send. So when the Arduino is sending data, that one is going to be turned on. RX is for receive. So when it's receiving data, then that one is going to be turned on. And, yeah, so that's about it for the layout of the Arduino board itself. There are actually other ways, or I should say, I'm just going to stop sharing my screen. Okay. So the Arduino we use when we're controlling hardware in our DIY projects, whatever it is. But there are other ways, or actually I should say this is like the brain, I guess, the CPU of your project. If your project is an analogous of a computer, this is analogous of the CPU. It isn't actually a CPU, but you get the idea. But there are other ways to control hardware components. For example, one other way, there are many, but one other is this one right here. This is a Raspberry Pi. You'll hear a lot of comparison between this and the Arduino. I personally don't think that's a completely fair comparison. They're very different. They're used for similar things, but they're very different. This thing is actually just a tiny computer. As I said, this is a microcontroller. This is able to just control whatever you have connected to these pins, but this is actually just a computer. You give it power with any like 5-volt cell phone charger you have here. You boot an operating system onto this SD card, which is slide in right there. Hello, Kevin. Then you have, I can't see that. How do I? There you go. So you also have an HDMI port. You can connect it to a monitor, and you have your USB ports. You can connect monitor, or you can connect a mice, keyboard, USBs. You also have Ethernet capability. So you can even see it kind of resembles the layout of a computer motherboard. So yeah, there's that. Just another option, another thing for you to learn about if you're interested. But anyway, let's go back to Tinkercad. So I don't know if I explained this already, actually, but you can create a Tinkercad account. Just go to tinkercad.com, and if you're in a computer engineering class, your teacher probably has a class code for you to use. So you're going to select this option. Otherwise, you can select this one or this one, probably this one. This one's better if you're a student anyway. And you can just sign in with your Google account. You can create an account with Tinkercad, and you can sign in with Apple, whatever you want. And then you're going to go, once you're signed in, you're going to see a screen like this. So Tinkercad can actually be used for 3D designs as well. The 3D modeling portion isn't that good, but the circuit part is the really good part. So you're just gonna go here to circuits, you create a new circuit, and you're gonna end up with just an empty screen, and you can just search here for components. You can search up Arduino, breadboard, whatever you want, and yeah, you can just connect everything here. So next thing to discuss is this thing right here. This is the breadboard. This is really useful when you're prototyping circuits that have pretty low gauge wires, because you can't run too much current through it. but especially with Arduino, this is a very useful thing to have. And so actually, if you look at what the inside of a breadboard looks like, so this is what it looks like in real life, just a bunch of pins where you put, show it on the camera. So you have these jumper wires. They have these pins. Yeah, there's the male side and then the female side, and you just connect it right into your Arduino, into whatever pin you want, and then the other side goes to your component. This is a relay, so you just connect it on like that, and yeah, that's kind of how you do it in real life. But in Tinkercad, it's much easier. You don't have to use your hands at all, or at least not no physical wires. So anyway, let's go back to Tinkercad. Oh no, the inside of a breadboard. That's what we were talking about. So this image right here, this is what the inside of a breadboard looks like. I'll open it up like that. So you can see these, all of these pins right here. They're connected, or when you're looking at it in this orientation, they're connected horizontally, or vertically. They're connected like that. And so if you have power going to this one, for example, that's going to power this entire rail. If you have power going to this one, that's going to do the same for this rail. And you'll see the zoom thing is in the way. So if I go back to Tinkercad, you'll see that I have the 5-volt and ground pins connected here. So all these rails are, or all these pins are powered. And I also have the wire going up to the other side. Reason I do that is if you have a wire going from here to here, you have power running through this, going all the way around here, and then through this. So now we have negative going on all of these pins and all of these pins, and then the same for the positive. You do the same thing. You just connect the wire from here to here. You don't need to do that. It's just it just gives you more more space to connect things. You can make it your circuits a little more cleaner, a little more clean. Then we have these pins here. They're all connected horizontally when you're looking at it in this orientation. So if you have power going to this one, for example, it's going to power all of these pins. But you see there's a gap in the middle. It's not going to, if you have power here, it's not going to power anything over here. So what you want to do, if you do want power going over there, you need something to connect this gap. So for example, the zoom thing is in the way. That is very annoying. But so on this circuit, there's a resistor that's bridging that gap. And otherwise, we just have an LED here that's connected by its anode to the positive rail. And then the, I didn't mean to click that. Okay. Then we have on the cathode side, we have a resistor that's connected to the negative terminal of the Arduino. So you'll notice that whenever we wire up components, at least in this orientation of the breadboard, we're always going to be wiring downward, because again, these pins are all connected that way. So if I have something like this, yeah, there you go. In terms of what components we're using, it's exactly the same as this. It's just all connected horizontally. If I start the simulation, you'll see that this one is going to turn on, but this one isn't, because again, they're not connected in that way. So there's that. Yeah, so that's it for the breadboard. Next, we're just going to look at this simple circuit that we have here. So it's just an LED, as I explained, it's an LED. And what an LED is, it's a light emitting diode. And so the important word there is diode. What a diode is, I can actually pull one up. This is a diode. This is what they look like. What a diode is a little component that only allows the flow of electricity in one direction. and that's indicated by this band right here. So electricity will only be able to flow that way, won't be able to come back the other way. It's like a check valve essentially. And so a diode does the same thing, or an light emitting diode does the same thing. It only allows the flow of electricity in one direction. The only difference is it lights up, and it works a little bit different. But so if I were to connect this terminal to the positive and this one to the negative, because it's a diode, it won't turn on because it isn't allowing electricity to flow in that direction. So you have the anode, which is going to be connected to positive, and the cathode, which is going to be connected to negative. The LED, as I explained before, cannot handle very much current before it explodes. So if I try this, if I just move this resistor out of the way and I try this circuit again, it's gonna explode. But since we're in Tinkercad, no risk of anything. But in real life, it wouldn't really be that intrusive. You'll just hear a little pop and the LED won't turn on, something like that. It's not gonna be a bomb. But anyway, so we have this resistor here, a 0.22 kilo ohm resistor connected to the LED, and so that limits the current, that keeps it from being damaged. So in its current state, though, the Arduino is essentially just acting like a battery. It's just applying a constant 5 volts. And there's so much more we can do with Arduino than just that. So we're gonna do a little bit of programming with it now. So we're gonna go ahead and connect the positive side of the LED to pin 9, for example. And the Arduino is programmed in C. I had some code here already. I'm just gonna get rid of that. So yeah, the Arduino is programmed in C++, and we typically, when you open up a new Arduino program, you're going to see these two blocks of code are going to be there just as by default. So what we have is the first part, which is setup, where we're going to set up all of our pins as either input or output, and set up some other things like the serial monitor we have down here. A lot of things we can do, just anything we'll do before we start sending any current through anything. And the void loop is what the code is going to loop through over and over again. This is where you have the code that does the stuff, essentially. I don't really know how else to put it. That's the best way I can do it, but that suffices. So first thing we're going to do is in our setup, we're going to set up this pin 9 as an output. So the way we do that is we do pin mode and then the pin number, which is 9, and we set that up as output, and that has to be in all caps. If it were an input device, we would put input in all caps. Then in the void loop, we're going to go ahead and we're going to give it a digital signal to the LED. So we're just going to do a simple circuit. It's going to turn the LED on for a second and then turn it off for a second. It's going to keep doing that over and over again. So I'm going to do digital write pin 9, and you write high for a digital signal. You can write high, you can write whatever its upper bound number is, but high is just so much easier to do. You just write high in all caps, and that will put it to its maximum value. Then we're gonna put a delay of 1000, and this is in milliseconds, so 1000 seconds, 1000 milliseconds is 1 second. So then we're gonna do the same thing. I'm just gonna turn it off. We're gonna write low, and then 1 second delay. Yeah, so let's go ahead and run that. I did not put semicolons anywhere. That's fine. Anyway, what's going on? Oh, okay, I didn't put it here either. Yeah, so there you go. The LED is just turning on for 1 second and then turning off for a second. It's just doing that over and over again. So that's all good. That's pretty simple though. So let's step it up a little bit. What we're going to try to make is we are going to have, I cannot do that. Okay. We're going to have 3 LEDs next to each other. Well, actually, they're all going to be wired up the same way, except their positive sides are going to be connected to different pins on the Arduino. So this one we're going to connect to pin 13. This one's going to go to 12. 12. I put 11. All right. 12. And this one's going to go to pin 13. I mean, 11. I messed up. Okay. It's 13, 12, 11 in this order. 13, 12, 11. So there you go. And what we want to get it to do is we want it to turn this one on for a second, then turn it off, and this one on for a second, turn it off, this one on for a second, and just keep going through that. Keep sequentially turning them on and off. So first we're going to do our setup, and we could just copy paste this line 3 times and put 13, 12, and 11 in this number. And if you have just 3 components, that's fine. But when you start having more, you want to be more efficient with your setup. You want to do it in the least amount of code as possible. So we can do that with a loop. Here it isn't completely necessary, but just to show how it's done, I'm gonna do it. So we can set up an array of ints called pins that we're gonna write 11, 12, and 13. These are our 3 pin numbers. And so in this setup, we are going to do a for loop. So for equals 0, I is less than 3, which is how many pins we have. I increases by 1 every loop. And we're just going to do pin mode pins index I. I'm going to set them up as output. So in this loop, it's going to set up all 3 of these LEDs as outputs. It ends up being probably more lines of code to do it this way when you just have 3 LEDs. But when, again, like I said, when you have this entire row filled up, it's for sure more efficient to do this. So yeah, there's that. Then in the void loop, we are gonna we're gonna do our for loop. So for at I equals 0, I is less than 3, number of LEDs we have. I increases by 1 every loop. I don't know why it keeps going back every time I do that. That's annoying. So we'll first just start out by, we'll try digital write pins. I do not put semicolons again everywhere. I need to stop doing that. I caught myself this time. So pins index I, and we're going to write it to its maximum value. And then 1 second delay. So we're going to write, actually we'll leave it at that just for now and see what happens. So if we try that, you'll see it turns them all off, all on one at a time, but it does not turn them off again. So they just turn on, as you saw, they just turn on pin 11, pin 12, pin 13, and they just stay on. But we want to have it as one turns on, we want to have the previous one turn off. So we're going to add this line in here. After it turns each pin on, then it turns the next one on, it's going to turn the previous one off. So there you go, pin 1 on, pin 1, or sorry, 11 on, 11 off, 12 on, 12 off, 13 on, 13 off, and it just keeps cycling through that. So there we have that, and you can do this with as many LEDs as you want. You just have to, or actually we could have replaced this with the length of this array. It probably would have been better, but let's say you have 5, you're just gonna change that number to 5. or again, just do length of the array, which is what I should have done, but it works, so that's fine. All right, so next we're gonna do a little bit of input. So I'll get rid of all this, just still need the setup block, still need the loop. I'm gonna get rid of all these. Gotta close the code before you can edit the circuit. So just gonna get rid of all of these. All right, so we're going to pick up this component right here, the potentiometer, which I explained a little bit before. It's a variable resistor. And this is one of the many analog input devices that we can use. It's a dial essentially. So if when you're in your car and you have like the volume knob, that is a potentiometer in there, or the temperature knob, whatever it is, it's a potentiometer. Or it may not look exactly like this, but it is a potentiometer. So we have terminal 1 and terminal 2. You'll notice that they aren't labeled positive or negative or anode and cathode like the diode was, because this isn't a diode. So you can connect these however you want. This on the negative, this on the positive. There we go. Then we have our wiper, which is where we send the signal to. Sometimes you'll see this pin called signal. For potentiometers, it's called wiper. It is what it is. So we can connect it to one of these pins. It would have to be one of the ones with the tilde next to them for the analog input. But like I said before, it's best with sensors to use these pins first before you start using those. We're going to connect this to A0. Oh, whoops. To bend the wires, you just right click while you're dragging it around. You can bend it, just make your circuit a little cleaner. So in the setup block, what we're gonna do is first we're gonna just define an integer called sensor value, and we're not gonna give it a value yet. That value is what we're going to read from the potentiometer. Then we're going to do serial.begin 9600. This is how you initialize the serial monitor, and it's at 9600 bits per second. So you got to do this if you want to be printing anything out to the serial monitor. You see, this is what it looks like. I had some stuff printing before, so that's what that's from, but otherwise it would be empty. So that's how you initialize a serial monitor. And then we're going to do pin mode again. So pin mode A0. And this time we're going to set it up as an input because this is an input device. So there's A0 set up and the serial monitor. So in the loop, what we're going to do is we're going to start getting values for the sensor value variable. We do analog read, and then we give the pin number, so A0. And we're going to print that out so we can see what those are. So we're going to do serial.print line sensor value. That should be good. We start the code and we open up the serial monitor. You see it's printing out to 0, and that's because it's at its left. It's a minimum state. So as we turn it around, you'll see the value starts to increase until it gets to its maximum value of 1023. Most output devices that you're going to be using will be either digital, or if they're analog, they're going to be using values from 0 to 180 with a servo motor, for example, or 0 to 225 with most other things. So we kind of have to do a little bit of arithmetic to get this value to the right number in order to use those in conjunction with output devices. But the point is that we have a value now as we turn the potentiometer. So now that we got that, next thing we're going to do, actually, I'll see if there are any questions. There are not, because no one is here except Kevin. Hello, Kevin. Okay, back to Tinkercad. So what we want to do now is we want to have some output device associated with this potentiometer. And one of the most common ones to use are servos. So if we grab a servo motor like that, we're going to want the servo, or actually I should explain what a servo motor is. So a servo motor is like a normal motor, except it's very, very precise in where you can move the axle. Typically, it's going to be anywhere from 0 to 180 degrees. You can't do a full 360, but sometimes, or at least with these 9-gram servos, it's 0 to 180 degrees. And the 9 grams, when you have servos, they typically have a weight associated with them. That's not the weight of the servo. That's how much torque they can provide from the axle. So it's typically going to be 0 to 180 degrees. And you can be very precise with where it goes. You can tell it to go to 90 degrees or whatever it is you want. But a normal motor, to do that, you need to have a motor controller with it. Otherwise, the motor is just going to be turning, and what you can adjust is the speed of it, not where it is. And actually, what a servo is actually just a small motor with a motor controller, and you can see a couple of gears in there. And there's just all in a little box. I'll show a picture of it. I grab servo. This is what they look like. You can see this little box, or you can't see it, but in the little box, there's a motor controller, and then you can see the gears. And so that's how it works. So for this servo, you see 3 pins, power, ground, and signal. Unlike the potentiometer and like the LED, it doesn't matter which where you place these pins. They are labeled power and ground. So power is going to go to the positive side, and ground is going to go to the negative side. Then our signal pin is a same functionality as the wiper, except it's for an output instead of an input. So signal is going to go to one of our pins at the top. So I'm just going to put it on pin 5. You should put it on an analog pin, because you want to be able to control where it is and not just 0 or 180 degrees. So there's that. Now servos are kind of special. You can't just set up the pin as an output and expect it to work. Servos they're special in the sense that Arduinos kind of suck at using them, as weird as it is to say. The 5 volts that you can get from the Arduino is enough to power just about 1 servo. But if you have more than that, the Arduino starts to have some trouble. Typically you can get like 2 or 3, but more than that, 3 is like the limit. 1 is where you can do it properly. If you go more than 3, typically you're going to have problems. And to use more than 3 with an Arduino, you need to have some sort of external power supply, like a battery or power supply unit, whatever it is. So to use servos, we have to use the servo library for Arduino, and this is how you import libraries in the Arduino code. So that's how you import that. And then we do servo dot my servo. So that's just creating a servo object, which is part of this library. So what you're going to do in this setup is myservo.attach, and then you type the pin that you put it to, which is 5, where we have it at. So myservo.attach 5, and then you're going to go. Otherwise, the code is pretty much the same. You have the input from the potentiometer, and you're just writing that to the Arduino. Except you'll see something is going to happen that I did explain briefly before, but I'll explain it again once it happens. So we're going to write to the servo sensor value, just the value of the potentiometer, and let's run that and see what happens. Actually, I should bring this to 0 first. Okay, so let's start turning the potentiometer. You'll see we've turned the potentiometer, I don't know, just in between its first two states, first two dots. They aren't actually states, it's just there's place markers, but we barely turned the potentiometer at all. That's the point. And the servo has almost turned halfway through its entire 180 degrees. It's almost turned 90 degrees. So if we bring it over here, that's pretty much it. That's all it's got. If you go more, it's going to start turning back. It's going to start not moving at all. You'll see there it starts to turn back. It's going to do some weird stuff, but we don't want that to happen. We want it to be able to go from here all the way to here. And this is the point where it reaches its 180 degrees. And so the reason for this, like I didn't mean to move that. Actually, I guess I can bring this there. It's back. The reason for that, I explained briefly. When we're looking at the potentiometer, you can see that it goes from, or well, you did see, yeah, it goes from 0 to 1023. But the servo only goes from 0 to 180 degrees. It takes a degree measurement as its input. So it only goes from 0 to 180. So we want some way to have this 1023 correspond to 180. The way we're going to do that is with a calculator. We're just going to go 1023 divided by 180. We get 5.68333 repeated. We're just going to go 5.7. That's good enough. So we'll go sensor value divided by 5.7. So let's run that, see what happens. We should bring it up to here, and it should be at about 90 degrees. There you go. It's at, now looks almost exactly 90 degrees. And if we bring it to the other side, it should go to 180. There you go. It seems to be working fine. So yeah, you can see we can control the Arduino's position with this dial input. And there are other ways to fix this issue with the potentiometer being 1023 and the servo's upper limit being 180. This is the most intuitive, I think. It isn't the best. There are ways to make it so that it moves faster, but for the sake of this demonstration, this is good. This is just an intuitive way to do it, and I think it's a good way to learn. So yeah, that's kind of the basics of Arduino. There's still a lot more that we can do. This is pretty much basically just surface level knowledge. I'm just trying to get you started with the basics, get you comfortable with the basics, so that you can start teaching yourself more. We only used a few components, but there are many more that we can use. So for input devices, we just search up sensor on the right side of Tinkercad. We see all of these input devices we can, not these, but all of these input devices we can use. And you'll see that a lot of them have either 2 or 3 pins. So let's get out the ultrasonic sensor for a minute. You'll see the way its pins are named, very similar to this. The orientation is different, but we're going to wire it pretty much exactly the same. So we can go 5 volts to the positive, and the ground will go to the negative, and the signal, I'm going to delete this one, but the signal is going to go to one of the input pins. So I'll put to A0. It's wired up almost exactly the same way. What an ultrasonic sensor is, it measures the distance from these 2 things. I'll show a picture of it. This is what it looks like. You'll see it kind of looks like a speaker, and there is a reason for that. the reason is that it pretty much is a speaker. What it's doing is it's sending out, it's called an ultrasonic sensor because it sends out an ultrasonic wave, ultrasonic being just a wave of sound that is above the hearing range of humans. So it sends out an ultrasonic wave. It knows the speed of the wave in air. And so it calculates how much time it takes for the wave to reach whatever the nearest object is and then return to it. And from there, it's just a simple calculation of the speed equals the distance divided by time. But actually, the distance is 2 times the distance that we actually want because it has to go to the object and back. So we will just divide that by 2. And that's how this sensor is able to calculate the distance to the nearest object. But wiring wise, it's nearly this identical in terms of code. It is also nearly identical. You just set it up as an output device. You have a variable for its value, and you just it's pretty much the same as the potentiometer. There's some differences in that this one will be taking in or this one will be giving a distance. This one will just give a number. So there are a little bit of differences in the code, but otherwise they're very similar. And you have the internet, so you can search it up, and you'll be able to find a lot about these sensors. Unfortunately, I can't go through it all in this one workshop, so you are left to the internet. But the internet is a great resource to learn all of this stuff. Then we can look at some more output devices. Go LED. It's either this LED that we used before. You can change its color to whatever you want. There's also this RGB LED, which is just another LED, but you'll see it has 4 pins. Reason for that is that you can supply current to, or you're going to have this one connected to the ground. This is a common ground, but the other ones, you supply current to each of them in varying amounts with the analog outputs, and it will mix the R, G, and B colors to create some other color. If you go to your go to Google and search up color picker, you can find any color you want here. Let's go some random color. This one, let's go that, and you'll see there's an RGB value: 67, 156, and 141. So it's combining this much red, this much green, and this much blue to create that color. So you can create just about any color with this. There are also diodes, which I briefly explained. There are capacitors as well. These are very useful devices. Capacitors, what they do is they store charge. They're kind of like batteries, but they function differently. They charge very quickly and they discharge very quickly. And these can be very useful. There's also transistors. Transistors are considered by some to be the most important electronic device. Computers are able to work because of this. This is like a physical representation of ones and zeros of bits. And what this does is it's an electronic switch. So you just electrically, it will close a circuit wherever you have it connected. It's a bit hard to explain, but the way a switch works is that you flip the switch and it just connects the 2 pieces of metal. This does the same thing, except you don't have to flip the switch. You just supply current to it, and it will flip the switch essentially. There are also relays. I don't know if we have any here. We have this one here, but let's put a picture of it. For sure, this one. This one's fine. Stuff like this. This does kind of a similar thing, but the way transistors work is that they manipulate the atoms directly. The way a relay works is it's just an electromagnet that's moving a piece of metal to connect the 2 terminals. But and that's how you can use. I explained earlier that if you want to use components that require more voltage, there's a way to do it. This is the way. So you can have like a 12-volt battery connected to a motor or a light bulb, whatever it is, if the 5 volts isn't enough. But yeah, there's that. That's it for the hardware portion of this workshop. So we'll just give it 5 minutes to and then we'll go into the computer vision portion. So just take 5 minutes to do whatever, Kevin. Okay, everyone, welcome to the computer vision portion of this workshop. I'm just going to share my screen. All right. So with computer vision, we're going to be using the OpenCV library. OpenCV is just an open source computer vision library. You can use it with Python, C++. Since we had the Python workshop, we're just going to go ahead and do it with Python. So the only prior knowledge you need for this workshop is Python. I'm using PyCharm right now. The reason for that is that PyCharm makes it really easy to install external libraries. If you aren't using PyCharm, you just go into your command terminal and do pip install, and the library name, it's either going to be CV2 or OpenCV. I'm pretty sure it's CV2, but I don't know off the top of my head, but just try both. But if you're in PyCharm, what you're going to do is go to settings under project and go to Python interpreter. So I have a bunch of libraries already installed. You probably don't have these if you're just starting out, but you're just going to hit the plus sign and you're going to search for whatever library it is you're trying to use. You can download OpenCV just on its own, but there's actually another library you can use called CV Zone. I don't know if you can install this through the command prompt. I haven't tried it, so I mean, maybe it'll work. Maybe just do pip install CV Zone. If it doesn't, then just use CV2, and that should be good enough. And any other libraries you need as we go along, you can just do pip install for those as well. So CV Zone is just a wrapper library that has a bunch of libraries within it that are very useful when doing computer vision. There's OpenCV is in here somewhere, a bunch of other ones. There's PySerial, NumPy, stuff like that. But anyway, so let's get started. The first thing we want to do is in this, you want to have a folder. Or actually, you don't need to have the folder in the folder, but you need to have everything, all the files that you're using for this this workshop. You want to have them all in the same folder. So I have the Python file that we're working on right now, and in the same folder as that, I have this media folder with a bunch of images in it. So first thing we want to do is just put one of these images on the screen. So we're going to go import CV2, and we're going to define our image. So image equals CV2.imread. Let's say the path, type the path. So it's media image.jpg. Very clever name, I know. And that is just some random image I took off Google Images. Literally just searched up images in Google Images and took the first one. So I don't know what it is really, but then we're going to go CV2 to display this image on the screen. The command is cv2.im show. This first string that we're putting is the name of the window that's going to pop up. So I'm just going to call it output. You'll see what I mean in a moment. And then we give the image that we're trying to output, the image variable. And then we're going to give it a delay. So wait, cv2.wait key is the command. This is going to be in milliseconds. So if you put like 1000, for example, the image is going to show up for 1 second, and then the program is gonna stop. But if you put 0, it will actually just display the image forever until you manually stop the program. So there's that. Yeah, the zoom thing is in the way again. There you go. Okay. So if we run that, yeah, you see this image, front-end image, very nice looking. And you see what I meant by the name of the window that's going to open. It's called output. That's what we called it. And so actually, I'll go ahead and just try the 1000 milliseconds. So you'll see it show up for 1 second, and then. So yeah, that's how you get an image onto the screen. Now, we also typically when we're doing computer vision stuff, I didn't do that. stopped. Typically, when we're doing computer vision stuff, we want to be looking through the webcam most of the time. We can also be like analyzing images or just videos, MP4 files, but webcam is what at least I do most of the time. So we're gonna get a webcam feed into Python. So again, we're just gonna do import CV2. And for a webcam, we're gonna do cap.cv2.video capture. And actually, you can do videos as well. I'll just show how that is. I don't have any videos downloaded here, so I'm not going to run it, but just to show you how to do it. So video and then video.mp4, whatever it is you called the video. Then you're going to do while true. Success, comma, image equals cap.read. And so what this is, it's going to save the video in an image variable, and the success part is a Boolean. It's going to return true if it did this all successfully. So there's that. Then again, cv2.imshow to put this on the screen. So we're going to give it the name output again. The variable is image. So what we want to do then is with videos, with the images, we didn't have the while loop because an image is just going to be one image just on the screen for however long we want it to be. But a video is a collection of images being displayed one after the other. So if we don't have the loop, it's just going to play the first frame of the video and stop there. So we have the loop to loop through every single frame. So we do if cv2.wait key 1. That's delay 1 millisecond in between frames. And this little bit, so it's not 0. What this is going to do is if we hit Q, it's going to stop running the program. So actually it's about to run, but I don't have any videos downloaded, so this isn't going to run anything. Okay, I actually need to show you the error message is going to pop up so you can see. This is the error message that you get when you have when you're referencing something that isn't there. But we want to get a webcam. So what we're going to do is instead of putting a string there, we're just going to put a number. Typically, it'll be 0. This is the ID of your webcam. If you have one webcam, it's typically going to be 0. If you have more than one, then you have to just cycle through the numbers, see which one is whichever one you want. But I only have one webcam right now, so we're going to put 0. And then what we can also do is this command right here, cap.set. We're gonna give it 2 numbers, so we can. I'll just do all of them for a moment, or just 2 of them actually. I'll do 3 and 4. So what 3 refers to the width, and 4 refers to the height. So we can set this to I don't know, some random numbers. I'm picking 300 by 500. Yeah, let's go ahead and run that. Wow, 300 by 500 is very small, actually. Let's go 1000 by, yeah, 500, we'll say. So there you go. You can see the webcam footage, webcam feed. So yeah, that's that. And we can do a lot of analysis of what's going on in the webcam. We can do this with videos as well. We can also do this with images, but again, typically you're going to be doing this most with webcam feed. So yeah, there's that. That is how you get a video or webcam footage. Next, there's some basic commands that OpenCV has that we're going to be using a lot. So we're going to go back to the image. So I'm the same one. So import the image again. And if you want to make this image grayscale, and there are reasons that you'll see later on why we do these kind of things, but you can change how the image looks. So you can make it grayscale. You can make a gray image. So cv2.cvt color, the image you're referencing, and then cv2 dot, and then all this is in caps, so color BGR. The reason it's BGR, typically, and actually when we're looking with the Arduino, we had the RGB LED. Typically, when you're doing color picker, you have one of the options is RGB for the colors. OpenCV does it in blue, green, and red rather than red, green, and blue. I'm not completely sure why, but there's just something to be aware of. It's going to come up later a little bit as well. So BGR to gray. So this is going to give us a gray image. So we'll do cv2.iron show output and then gray image. Do a delay again. So cv2.wait key 0. So just an infinite delay. So you can see we have the same image, but it's gray as you would expect. So there's that. But there is also more we can do. There are a lot of commands. I'm not going to go through all of them, just a few of them. So another one we can do is a contoured image. So what this is going to do is it's just going to basically just highlight all the contours of the image. And you'll see what I mean in a bit, and I'll explain how it works in a bit as well. So cv2.canny image, and we give these two values just to like how, I guess, how strict, not really trying to phrase it, but how strict it's going to be with the contours. I'll change the values and you'll see what I mean. Actually, I'll put it to be 100. And so if I do contoured image, I spell it. See, oh, contoured, not contoured, contoured. Okay. So you can see it just looks at all of the like lines, I guess, in the image. The way it does this is it's analyzing each pixel, and it's seeing that so maybe here for the water, maybe a lot of them are blue, a lot of them are like very close to each other in their color and their BGR value. They're all some shade of blue. But then when it gets here, it goes to a color that's very dramatically different. So it recognizes that there should be a line there. So it draws that line, draws that line. That's how it's working. And I can show you what these values do, kind of. So do 150 and then 200. So 100 again. You can't really see there. Let me pick different values. Yeah. So here you can see very dramatically, it's not picking up many of the contours. It's being very not sure the word. The word is right there on the tip of my tongue, but it's being very strict, I guess, with what it's defining, what it's declaring as a contour. So we're gonna go back to 150, 200. So there is the contoured image. We can also resize the image. So resized image equals cv2.resize. We'll go 1,000 and 300. And these are in pixels, by the way, so it's 1,000 pixels by 300 pixels. What? Oh, I didn't give a. I don't know what to resize now. Actually, you know what, I'll go ahead and make the gray image. I'll resize the gray image. Did I spell that wrong? Yeah, capital I. Okay. So it's going to resize the. What happened? Oh, this should be a point, or not a point, but an ordered pair, I guess. I'm lost, but there you go. So yeah, the gray image has been resized to 1,000 by 300 pixels. So again, there are many more commands you can use, but there's just 3 of them. We'll go over a few more later as we need them. We're not going to go through all of them though. But yes, that is that. Next thing we're going to do is so I have this. I wonder if I can open it right from here. No, not that one. This one. Image did not load. Okay, I guess I'll just share this then. Yeah, you see this image right here with all of these cards. So if you've ever used a scanner, like on your phone, just to scan a document or whatever, we're gonna try and do that same sort of thing here. We're gonna try and isolate for this this Jack card and have we're gonna have one window show this entire image and the other window just show the Jack card, and it's gonna be upright. So let's start doing that. So to do this, we're also going to need to import NumPy. So we're going to go NumPy as NP. So image equals cv2.imread media cards JPEG, and we'll set the width and height. Yes, I spelled it correctly. These are going to be the width and height of the second window we're going to open, which is just the card alone. Make it 250 by 300. So the way we're going to do this is we need to have first an array of points that, I guess I'll just show it like this. So if we go into Paint, or if we open that image in Paint, you'll see when we move our cursor around on the image in the bottom left, right over here, you'll see an ordered pair of points of where it is we have our cursor. So this first array, or this first list, is going to be a list of the points of each of the corners of this card. So we're just going to hover our mouse over here and get whatever point it is we're trying to look for. We could also just take a point here, for example, here, here, and here, and it would end up just giving us this little area right here, but that's not what we're looking for. We're just looking for this card. So you get the points where each of the corners are at, and you put them into this array. I already got them, so I'm not gonna go through that again, but the points are, so the first one is, oh, sorry. So, and again, I just got these from looking at the image in Paint, so. Okay, so I'm gonna open up the image again. So these points are in the order in which they appear. It's this corner. Wait, I believe if I remember correctly, it was this corner, this corner. Was it this corner? This corner, or this corner? It's either this one, this one, this one, this one, or this one, this one, this one, this one. Although it doesn't completely matter in which order you pick them, as long as you're aware of which order you pick them. I have all these values already taken because this is kind of a pain to go through again to get all these values, but I explained how I did it. So these points, the second list of points is going to be where each of these points corresponds to on our second window that's going to show up. So this point, which is the top left, is going, the top left of the card is going to be 0, 0 on our second window that's going to show up. So that one is going to correspond to 0, 0. The second one is going to correspond to the width of the, so this width that we defined here, the 250, 0. So that's the top right corner. Then we have the next one is 0, and then the height So the X is, it's 0 in the X, and then it's going to go 300 down. So actually that tells me then that this third point is the bottom left corner. And then the last one is going to be the width and then the height. So it's going to be going the width of the window to the right and the height of the window down. So that's the bottom left of the window. We need to make a matrix of these points. So we're going to do cv2.get perspective transform, and then the first list and the second list. Then we'll go ahead and print that. Then we're gonna create our image. Oh, sorry, I can't divide image again. Output cv2.warp perspective. The original image, the matrix that we just made, and the width and height of the second window. Then we're gonna show this on the screen. So cv2.im show. We'll do first the original image with all the cards next to each other. So all these cards. IM image, and then the next one will be the Jack card on its own. Output and infinite delay again, so that they don't read us too quick. There you go. Oh, sorry. Good. Chat message. Why is my screen so small? Is it? What do you mean it's small? I can tell. Just send it in the Discord. We'll just cut this part of the recording out. Okay, where were we? Okay, yeah. Recording is going on, right? Yes. Yes. Okay. So yeah, let's run the code then. That's not right. Am I gonna have to find the points again? That would be not really fun. But, okay, what did I do wrong? Did I do anything wrong? Why is this not working? What does it look like? Okay. You know what? I'll just find the points again. So yeah, we're gonna do what I did not want to do, but we'll find the points again. Maybe I found them wrong. Okay. So the first one is, yeah, it looks like I did it wrong. 223.91. The second one is 431 and 140. 431, 140. Next one is the bottom left. So that is 161, 381. Doesn't have to be exact, exactly on the corner, especially since it's a rounded corner. And there's 371 and 430. should work. Yeah, there you go. So yeah, I guess I just got the points wrong, but now you've seen how I got the points. And yeah, there it is. There's the jack on its own. It's a little bit wonky, but the points weren't exact. So if I took a little more time getting the points, then they will be fine. But according to that, it works. And this is how scanner software works as well. We can actually make a scanner software from something from our webcam using something like this. So we are not going to do that, but just you can do that, just so you know. All right, let's go to the next thing, which is we have another image in here. This one, just a bunch of shapes, and so we want to be able to detect what all these shapes are. So the program should be able to recognize this is a triangle, this is a square, and all that. So first, what we're going to do is we need our contoured image, like we showed earlier with the basic functions. So the contours, comma, hierarchy equals cv2 dot find contours image cv2 dot pr external and cv2 dot. So what this is doing is we have the image. Oh, sorry, this is supposed to be a function. I didn't define the image. This is a function that we're making called get contours. Contours again, contours. We're going to be inputting, giving the image our input. So there you go. It takes the image. With this bit here, this is the retrieval method for all of the extreme outer contours. So in this case, like I explained when we did the contours before for the shapes image, it's very clear where the computer can very easily tell where the edges of the shape are. It's just it goes from black to white, so it's very clear. But with some more I guess some more complicated looking images like the image.jpg, this one, it would need to be a little more thorough with how it's finding the contours, because it's not as obvious as it is there. And this one is whether or not it will approximate the points where the contours are, and we don't want it to, so there's that. Then we're going to go, and this is a list object. This is getting all of the contours of all the objects that it can find. So we're going to go for contours. We're going to find the area of each of these contours. So cv2 dot contour area, another function that we have in OpenCV. So area equals cv2 dot contour area, and we give each, it's going to look for this for each contour within the list. And we'll print the area as well. So print the area. We don't want it to, if there's like any imperfections with the image, we don't want it to be picking up little things that just little, I guess, specks of dust maybe or something like that that's on the image and mistake that for a shape. So we're going to say that it will only find the contour if, or it will only draw the contour if the area of the object that it's found the contour for is greater than 500 pixels. So cv2 dot draw contours. Wait a minute, image. Okay, so we create an image, contour image. It's not right. Okay, well, we'll see what error it gives us if it does. Okay, we can just I'm going to be looking at each contour. And so the -1 means that it's going to be drawing all the contours. This next this bit here is the BGR value. It's going to be in BGR, not RGB. It's just the color of the contour that's going to be drawing. So this one is 255 on B, then 0, 0 on green and red. So it's going to be blue. And it's going to have a thickness of 2 pixels. Find the perimeter of the contour. So we call cv2.arc length. Arc like contour. And we'll print the perimeter. And then it's going to be making like approximating what the contour is going to look like, especially if you have like dull edges and whatnot. This is useful, so prox. And that bit that 0.02 times the perimeter is the resolution. And then it's tour. So we'll print the number of contours that we see on the image. And typically, or actually not typically, with this specific image, I'll open it again. We have squares, triangles, and circles. So we have three corners, and it would see that and recognize that it's a triangle. 4 corners, it would see as a square. But for a circle, it would see pretty much like as many pixels as there are. I could say infinite number of corners, but there would be a number to it because it will just look at all the pixels. But either way, it's going to be greater than, much greater than any of these. So we say that if it's, we'll say that if it's greater than 4, it's going to be a circle. So we're going to have a rectangle drawn around the shape. And that's essentially what this is. It's going to be the rectangle is drawn around the shape, where we're going to have the text above that indicates what it is. So yeah, we're just defining, like I said, what the shape is. What the shape is, given how many corners we see. And we want to be able to differentiate between squares and rectangles. So it's just finding the ratio of the width to the height. If it's a square, it should be 1. It might not be exactly 1. There could be some imperfection with the image. So we give a relative error of 0.05. And then if it isn't, the ratio of width to height is not that, then we can say that it's a rectangle. And again, if the the number of corners is greater than 4, we're going to say it's a circle because 4 is our maximum number of corners. And if you don't know what the maximum number of corners is, you don't have to put 4. You can just put like some absurdly high value, because the circle is just going to have an absurdly high number of corners. So unless you're unsure if you're going to be having a shape with, I don't know, like 1,000 corners, you can just go ahead and put that. And if you have a shape with 1,000 corners at this point, is it really anything but a circle? So, yeah. And if it doesn't fall into any of those categories, we'll just say it is not a shape at all. For this case, that's okay, because we know what we're looking for. So we're going to create the rectangle. I have something missing, I think. Okay, we'll see. So we're going to go ahead and start drawing all the rectangles there. And those are going to be, yeah, we'll make them red. We're also going to put text on top of the rectangle to show what the image is. So image and then object type. Chat message. Okay. Yeah. Well, you have a question or anything like it? What do you mean? Did I mess something up? All right. Okay. So this is going to be just the position of the top left of the text. And this one is going to be the font. There's some default fonts that we have in OpenCV. All of these. I'm just going to go with the first one. It doesn't matter that much. And the thickness of the text. And then also okay. So yeah, we have that. So let's go. We don't need that. Let's go image. Just like we did before, we're going to define the path. Wait a minute. Okay, well, whatever, we'll see what happens. I create a copy of the image, which we're going to have the contours on. Then we're going to make a, oh, sorry, we're going to make a grayscale image. Yeah, this is one of the situations where we're going to be using the basic functions that we taught earlier. And then we're also going to have a canny image. And we're going to put that on the gray image. Sorry, the speed. And then we're going to do get contours on the canny image. So get contours and canny image. I actually don't need that, but let's do cv2 to im show. I think this will give an error, but we'll see. And 0 delay. So let's see what happens. Yep. Okay, that is not working how I intended. I'm just going to stop the recording while I figure this out. Okay, so I see what's wrong. I forgot to put image contour in a few areas. So if I run it now, you see that the contours show up. Find out where else I did not include it. I think that should be it. Yeah, there you go. Okay, so yeah, I just forgot to put image contours, which we had to find down here, right here. But yeah, everything is working now. Okay, there you go. So yeah, it's able to identify all the shapes. So as these triangle, circle, it got me wrong. Doesn't seem to have. Yep, everything seems to be good, and it isn't identifying anything that isn't a shape. So that's all good. Yeah. Okay. There's the shape detection bit. Now for the final thing we're going to do is we're going to do a little bit of face detection. That's fun, isn't it? So this is probably one of the most common things you can do with the, I saw the covering. One of the most impressive things you can do with computer vision is be able to recognize a face. Now, recognize, what we're going to do is just identify that, or identify a face. But you can go even further with that and recognize recognize an actual person. So, for example, you can a lot of cars, well, I don't know what cars it is, but like on cell phones, when you have face detection, what that's doing is it's looking at you, and when you set up your face or your facial recognition, you essentially just go around your face with the camera. You take a bunch of, it's essentially taking a bunch of pictures of your face, and there's a machine learning algorithm. So it recognizes certain features about your face, like the shape, certain imperfections you have on your face, stuff like that. And it's able to through that it's able to recognize who you are. We're not going to be going to that because that's a lot of work, and we simply don't have the time for that. But that's somewhere where you can go further than this. With this, we're just going to be detecting a face. So let's get started with that. So again, we are going to be importing CV2. And there is a folder here called Cascades, which has, I'll scroll over a little bit. You can see all of these computer vision models that have been are pre-built into OpenCV. You can see there's stuff for, you can recognize a smile, a Russian license plate for some reason, full body, left eye, lower body, stuff like that. There's a bunch of stuff. We're going to be using the face one for now. You can use any of these for whatever you want. You can also train your own. The way you do that is, as I explained, how your cell phone recognizes your face, is you take a bunch of pictures of whatever it is you're trying to detect. And you take a bunch of pictures of stuff that just isn't that. So the computer vision or the model will be able to recognize certain features about what it is that you identify as the object that you want to detect, and it recognizes features about what isn't the object. So, for example, a while ago I was working on a project where the camera would be able to detect, would look at a tomato and it'd be able to detect whether or not the tomato was was ripe, essentially. It'd also be able to detect when it was rotten. So it would look for things like the color, the shape, the sheen. And for the rotten tomato, for example, it would see that it was wrinkly. It kind of had some black spots, stuff like that. And you do that by just gathering a bunch of images of ripe tomatoes, unripe tomatoes, rotten tomatoes, stuff like that, or whatever it is you're trying to detect. And thankfully, you don't have to just go with your cell phone and just take a bunch of pictures of like hundreds of pictures. Typically, you want to go in the hundreds, take hundreds of pictures of whatever it is you're trying to detect. There are ways to take these images very quickly. For example, there's this website called Teachable Machine, which makes it really easy to make these computer vision models. But these ones we have here are all pre-built in OpenCV. So we're going to use the face one. So we'll go face cascade equals CV2 dot cascade classifier. And then give the path for the cascade. So we've defined our cascade, and then the image is going to be cv2.imread. And I have an image of the one and only J.K. Simmons that we're going to use. There's jksimmons.png. And then we're also going to make the image. We're going to take a gray version of the image as well. So gray image equals cv2. The reason we take the gray image is it just makes it a little bit easier for the computer to recognize the image. If you have a bunch of colors going on, it's much easier for it to recognize the difference between light gray and black or white than it is between like a red and a black, something like that. We're going to apply the cascade to the gray image. There it is. This is the scale factor. These last two numbers I put in, this is the scale factor of the image. So for the dimensions of the window, or sorry, not of the window, of the face it's detecting. So it's going to again put, like we did the last one, it's going to put a rectangle around the face. So the dimensions of the rectangle. So cv2.rectangle image x and y. X plus the width, so that is the top left, and then y plus the height. Oh, actually, I don't know if I mentioned this before, but I should. So this is the image we're going to be using. J.K. Simmons, as I said, wonderful actor, with OpenCV, and actually with a lot of Python libraries that have some sort of graphical interface, like Pygame, stuff like that. The convention for the points is not the same as the standard like Cartesian system you learn in math. 0, 0 is actually up here, and then the width of the image, comma 0 would be over here. The 0, comma the height of the image will be here, and this will be width, comma height. But the point is that 0, 0 starts in the top left rather than the bottom left, like you would expect in a normal Cartesian system. Then this is going to be the color of the rectangle. It's going to be a shade of green. The width of the rectangle. So we're going to also put text above it to recognize, to just say that this is a face. You know, it's just going to say face. So image, and the text is going to be a face again. So x minus 5 is going to be on the top left of the rectangle. So y minus 10, and then cv2.font. Let's go with the first font. And then we're just going to show the image. So I'm show. since we don't want the gray image to show up, we're doing all these operations on the gray image, but we can just put the rectangle on the original image given the position of the gray image, because they're the same image, just different colors. So that works fine. That infinite delay. Let's go ahead and try that. Something went wrong. What is the problem? Where does it say the error is? Line 7. So it's here. Probably misspelled something. CASCADE. That's good. Why isn't it working? Let's see. Let's stop the recording again. I want to try this. Okay, so the error was I just misspelled this. It's called Cascades and not Cascade. I thought the error was over here, but there you go. So it should work now. Yep, there you go. This should be. There you go. So it's able to detect the face. And we have the face written in green, or we have face written in green above on the top left of the rectangle. So yeah, there you go. And you can also implement this with the webcam footage as well, which is kind of what you want to go for rather than just still images. And you'll be able to recognize your face live on the webcam feed. Not going to go into that for this lesson, but again, this is to give you a good basic understanding of computer vision. You understand kind of the basic functions that you have, what you can do, sort of. But again, there's a whole lot more that you can do with OpenCV, with computer vision. It's a very powerful tool to have, and I highly recommend you. I mean, the internet's a great resource to learn this. I highly recommend it if you want to continue learning. There is one YouTube channel, Murtaza's Workshop, so just so you can spell it out, or so you can know how to spell it. This one right here, Murtaza's Workshop. Really good place to learn computer vision, robotics, machine learning, stuff like that. It's a really, really good channel. Well, mostly for computer vision, but yeah, it's pretty good. Anyway, that is it for this workshop. The recording should be up soon, next week, hopefully. And the Discord should also be ready very soon as well. And you can ask questions that you have in the, we'll have a specific text channel for this workshop, and every other workshop will have a specific text channel where you can ask any questions that you have in the channel, and any of the other participants or any of the organizers can help you out. So yeah, there's that. The event, the hackathon, is in 2 weeks, so good luck on your submissions. All right, yeah, that's it.